Report of a fire. Engine 9. Medic 8.
Hey, I want to welcome you to air monitoring class, and again we're recording this so that it can go on CenterLearn. Specifically, a number of years ago, NFPA created a new level of training, if you would. So instead of just having awareness, operations, technician, specialist, and incident commander, they created a number of things called mission specialties. One of the mission specialties that can happen anytime after the operations section is air monitoring. So we want you guys familiar with, we want a better understanding of how to operate those P400 meters. Also, because of some problems with those P400 meters, we want you to get a better understanding of exactly why they're giving a reading every now and then and what that reading may or may not mean. So specifically, at the end of this unit of training, each student is going to demonstrate the knowledge and ability to operate the authority having jurisdiction or Columbus Fire's specific air monitoring equipment. The student performance objectives is going to be able to select and detect or use an air monitoring equipment suitable for detecting monitoring of gases. So we want to be able to monitor gases on the scene using our P400. We want to know the operational capabilities and limitations and the local monitoring procedures, field testing and maintenance for that P400 5-gas meter that is on the trucks. We want to be able to demonstrate field testing and operation of each device to be used to interpret the readings, and we want to demonstrate the ability to operate under Columbus Fire's direct reading instruments. So lovely. We got about a 30-minute lecture that we're going to do. Then we're going to ask you to get your P400 meter and go through it so that you can be better familiar with what it's doing, how it's operating, how to turn it on, how to turn it off, and any problems that are with it. NFPA, as I said, the National Fire Protection Association writes standards for hazardous materials response. The City of Columbus says we are supposed to be able to operate under those standards. All of the NFPA standards are written under an acronym called a PI. So what they do is they give you general requirements for this position. This class is actually taken out of the mission-specific competency of air monitoring. Then it goes into analyzing the incident. When we arrive on the scene, the first thing we're supposed to do is recognize, identify. We're supposed to come up with a potential plan for isolating and protecting people. We're supposed to make sure that we make all the proper notifications. And then the final thing is we stand up and say, hey, I'm in charge until somebody else gets there. So those are the awareness level standards or requirements. NFPA says that's part of the analysis, analyzing what's going on. After I analyze, then I have to plan my response. I have to come up with a plan of how I'm going to be able to operate within this scene, and then I'm going to implement that plan. So after I come up with my ideas of what to do, I'm going to actually implement it. Then I'm going to evaluate the progress, whether or not I'm getting the results that I anticipated, whether or not things are getting better. And then finally, when everything is solved, we terminate the incident. So in this, with our air monitors, NFPA is again using these guidelines. We should know how to use an instrument. We should understand what the instrument is doing for us. We should understand how it's going to change our response plan. We should realize, based on readings, how we can change the level of PPE we're wearing or setting up of a hot zone or items like that. So as an introduction, the mission-specific competencies say, first off, we have to work under the guise of a hazmat tech. So we're always available at Station 4. You can call us if you're having a problem or if you're getting a reading that you don't understand. And that's really how we meet the goal of working underneath that hazmat tech or allied professional. Wearing the appropriate PPE. Remember, an air monitor cannot guarantee to you that the atmosphere is safe. An air monitor can only tell us what we think we already know. And so when we're monitoring unknown atmospheres, when you have sick or ill people, the critical thing is to make sure we're wearing our PPE or our personal protective equipment, or in our cases, our firefighting protective clothing and an SCBA, and the SCBA should be hooked up and you should be breathing air from the bottle if there's a concern that there's something in the atmosphere that's really causing a problem. The main thing I cannot stress enough is the air monitor cannot tell you that the atmosphere is safe. It can only tell us what we think we already know. If we think the atmosphere is safe, if we have no reason to believe the atmosphere isn't safe, then firing up the air monitor and determining that all of the readings are normal is pretty much an indication that you're right, the atmosphere is safe. But I can kill you with chemicals that are at a level that the air monitor cannot pick up. And I'm not saying that to be grand and glorious or over-exaggerating. I'm just telling you the fact. The air monitor will not pick up everything that's potentially in the atmosphere. If I have dead people and the air monitor says everything is normal, ignore the air monitor. Go with the signs and the symptoms of the people that are there. We should have a plan. Our plan should include going in and investigating. Our plan should include the fact that, remember, the air monitor has to be held high in the air at times. It's got to be tested down low. It can't be carried real close to the body, because if I keep it real close to the body, I'm going to eliminate its ability to really be testing the air. And these are things I'm going to cover again here in just a minute. Real-time air monitors. There's a reason why we use real-time air monitors. Real-time air monitors are a great benefit. When we first started our hazmat team, some of the air monitors we had were pretty large in size. Now we're able to deal with air monitors that are very easy to handle, very easy to operate, and they can give us good information. First thing, we can use the air monitor to assess our health risk. Bruce, will you throw me the air monitor that's right there behind you? Okay, great. We can use these air monitors to assess our health risks. When we're getting readings on this air monitor, when we're getting parts per million of carbon monoxide or hydrogen sulfide, when the O2 is not normal, really we can verify and say something could be in the air, and that's a way to assess our health risks. So we can use this to tell us if the atmosphere is potentially bad. We can use air monitors to select and verify our levels of PPE. If the air monitor is telling you there's the presence of something flammable, what it's really telling you is you better have on firefighting protective clothing and an SCBA, because whatever is in this atmosphere can potentially ignite and catch fire. If on a hazmat incident we're using the air monitor and we're wearing plastic suits and we get LEL readings, it's telling us that you're not in the right level of protective clothing and it's time to change your level of protective clothing. So again, I can assess my health risk. I can also make sure I'm wearing proper levels of PPE. If the O2 is not exactly what it's supposed to be, it's an indication that I need to have some kind of respiratory protection on. I can also use it to figure out my work zones. So if I get a reading of 0 here, and I take 3 steps forward and I get a reading of 3, whoa, okay. Well, why did I do that? And I step back and I don't get any reading, and I step forward and I get a reading of 3, and I step back and I don't get any reading, then you can see I could easily draw a line right here, put up a piece of barrier tape and say, hey, that's my hot zone, this is my cold zone. And so I can delineate the work zones by using the air monitor to figure out exactly where the chemical or where the problem might be. I can determine where the chemical is going. Again, I can help figure out where the chemical is moving to and moving from. So if I don't get any reading here, but I walk farther in and I get a reading, or I walk downwind and I suddenly get a reading, I can tell you which way that chemical seems to be going. Remember that chemicals have vapor density. That means some chemicals, and they're very few, are lighter than air. They're going to dissipate upward in a room. So if I'm on a natural gas leak, I want to keep my air monitor as high as I can to see what's at the ceiling. But propane and most of your other chemicals are heavier than air. So if I'm on a potential propane leak, then I want to keep the monitor as low to the ground as I can because that's where the propane's going to go. The propane's going to head to the basement, natural gas is going to head to the attic. I can help verify that by utilizing the air monitor. I may not get a reading at chest height, but I may get a reading up high or down low. I can also use the air monitor to select mitigation techniques. Okay, you arrive on the scene, you're first on the scene of a tanker incident and you have potentially gasoline down or ethanol, and you grab your air monitor and you get flammable readings. Well, the flammable reading is verifying to you that, hey, this could be gasoline, it could be ethanol, and it's going to suggest to you we want to eliminate those vapors. And so we could foam that liquid product, and once we foam it appropriately and it eliminates the vapors, we could actually verify it by using the air monitor and walking around the area and verifying that now I'm not getting any particular or potential reading of LEL. Then in 15 or 20 minutes when the foam blanket starts breaking down, the air monitor is there to tell you, hey, it's breaking down because you're beginning to get LEL readings again. So again, these monitors are fantastic. They offer us a lot of benefits. But the problem is, if you don't understand the air monitor and you don't understand what it can't tell you, then you'll think this air monitor can tell you that an atmosphere is safe when it can't tell you that atmosphere is safe. The more I understand about the air monitor, the better the tool it's going to be. But if you think you can walk into a totally unknown atmosphere, turn this thing on or walk in with it and determine that the atmosphere is safe, I can take off my SCBA, you're wrong. You can't do that with these monitors. And that's the main focus of preaching to you this morning. And then we'll get into the specifics of how to use that particular air monitor. Okay, great. NFPA says there's 18 different types of technology that we can do in air monitoring. We're only going to talk about a couple of these this morning, but we have a wide variety of these technologies down at Hazmat 4. At Hazmat 4, we've got advanced air monitors that are going to use some pretty tricky technology to help us to even identify unknown chemicals. Air monitors. What makes air monitors valuable to us are these things right here. First off, portable and rugged. We're firemen. You all know that our goal is to drop this and see what it does. We always drop it no matter what. These are technical instruments, but they have to be rugged. Portability. Gosh, this is small. It's obviously portable. When I first got on Hazmat, yes, as an old man, back in 1989 when we created the team, a mass spectrometer was literally the size of one of these tables. We had maybe 3 or 4 of them in the city, and obviously they weren't of any use to us on the Hazmat team out in the field. Well, now we carry mass spectrometers in our hand that can identify unknown chemicals. So portability is not an issue anymore. We have chosen an air monitor. That P400 is obviously portable, and obviously it's reasonably rugged. The next is easy to operate. Easy to operate. I always judge an instrument on my ability to pick it up and turn it on and get it to work without having to read the owner's manual. Because I know, unfortunately, most of you guys out there are not going to read the owner's manual. We'll talk about turning it on. We'll talk about fresh air calibration. We'll talk about anything else that needs to be done to this in the second part of this series. But I need to know how to operate it, and it's got to be relatively easy to operate. Inherently safe. As you guys realize, I would not want to take something into a potential gas leak that could ignite that gas leak. So they have to be inherently safe. We don't want this to ignite the atmosphere that we're doing. Inherent safety. It has to do with the class or the atmosphere that they tested in and the products that they test. Reliable and useful results. Well, the reliability of it. Will it tell me what I think it's telling me? How accurate is it on what it's telling me? We're going to go into much greater detail on reliable and useful results, but the main thing I'm trying to emphasize is these are not reliable. I cannot trust them. But the more you know about these instruments, the more you can trust them and the more you can rely on them, because the more useful the result is. So if I understand how it works, I understand what fools it, then I can make a better decision of whether or not I trust it. And that's the emphasis. We cannot trust these instruments. They only tell us what we think we already know. And I'm not bashing any instrument. It's just the requirement of understanding exactly what it can tell us and what it can't tell us. Okay, reliable and useful results. In order to have something reliable, in order to have a useful response, then I have to understand the instrument. The first thing up there is the response time. You have to understand how long it takes for this unit to respond. So you can test that by breathing into the sensors and seeing how long it takes before the O2, which just changed, to read. So the O2 sensor takes 3 or 4 seconds to read. Well, that may be a really quick time, except if I'm moving through an atmosphere. And you can see if I walk into a room and I'm walking relatively rapidly, I could hit a bad atmosphere here, but at 1,002, 1,000, it may not read until here. The atmosphere isn't bad here. The atmosphere is bad 3 seconds ago. And now you may go from a relatively not too dangerous atmosphere into a deadly atmosphere by continuing 3 or 4 steps. So, response time. How long does it take for it to respond? The rescues have these units with a pump attached. That pump will increase the amount of time it takes for it to respond. So if I have 20 foot of tubing on this, I have to realize that it's going to take even longer for that tubing to get into this and for the instrument to actually give a reading. Slow down. If you are used to carrying the monitor right here, if you hang it on your fire gear and look at it, remember, all you are monitoring is the air in front of your fire gear. As you walk, you can push this air right with you, and you're not monitoring the air in the room, you're monitoring what's right here in front of you. In order to get a good reading, I want to hold the air monitor up here and wait 3 seconds. I want to hold the air monitor all the way at the bottom and wait 3 seconds in order to get the reading and then move on. Now that's going to slow your response time down, or it's going to slow your response down. But again, if I hang it here and I walk in, I'm not really reading the atmosphere in the room. I'm reading the atmosphere that's 6 inches in front of my fire gear. If I'm not getting it into new air, it's not telling you anything but what it already knows right here close to you. That's your response time. Sensitivity. How sensitive is it? Sensitivity is really telling you how many parts in a million parts of air can this smell? How many parts of a bad chemical in the air does it take to get it to change? Okay, 3 of the sensors on this, carbon monoxide, hydrogen cyanide, and H2S, is relatively sensitive. It measures in parts per million. So when I get a reading of 1, it's telling you there's 1 part in a million parts of air. So that's sensitive. But the O2 meter is not sensitive. It measures in percentages. And it's telling you it's 20.9 is normal oxygen. Well, the drop from 20.9 to 20.8 requires 1,000 parts per million of oxygen to disappear, because each 1% is 10,000 parts per million. It's not sensitive. The air monitor, as far as oxygen goes, will never drop if I put you in an atmosphere of 200 parts per million of some deadly chemical. And it may not be readable any other way. So you cannot trust the O2 meter as being sensitive. The LEL meter is the same way. The LEL meter reads a percent of a percent, and that means it's a little bit more sensitive. It's going to drop to 100 parts per million before it makes a change. But again, what I have to understand is that sensitivity isn't there. We carry air monitors at Hazmat 4 that are much more sensitive to certain types of products. If I understand its lack of sensitivity, I'm going to be able to trust it better. Amplification. Amplification is a term that basically means how does the instrument take a small quantity of something and change it or amplify it to the point where now I can get a better reading on it. Amplification many times will deal with radiation monitors, and we'll have to deal with the radiation monitors when we do that training program, when we get our new Radiacs or our new radiation monitors. Accuracy. How accurate is it? Meaning, if it's measuring 3 parts per million of carbon monoxide, is it really 3 parts per million of carbon monoxide, or could it be as many as 10 parts per million or as little as 2 parts per million? And so I want to know the accuracy of it. Again, the problem with these instruments is they are not accurate. They all will tell you there's a certain percentage point to their accuracy. And so I never want to look at 3 parts per million as being exactly 3 parts per million. I just want to know it's somewhere, and I want to know that a reading of 3 is a little bit less than a reading of 5. Precision. Is it exact in what it's measuring? The next big problem with this is realizing that this meter does not know what it's smelling. It does not know the difference between carbon monoxide or hydrogen cyanide or hydrogen sulfide. It doesn't know the difference between that. There are chemicals that will fool these sensors. So when I get a reading of 3 on the carbon monoxide monitor, I can't stand up and say, oh, there's carbon monoxide in this room, because it's not precise. It may not be exactly accurate. It may not be precise. There could be another chemical in this room that's fooling this sensor. Once again, the more I know about these, the more I can trust them. The more I think they're telling me information that they're really not telling me, I can't trust them. I'm liable to get myself into a dangerous situation. Selectivity. Selectivity is the ability to change its accuracy or change its precision. Our instruments, the P400, we really can't change the selectivity on it, so we don't have to worry about selectivity. But again, we do have instruments down at Hazmat 4 that we can actually change the selectivity. The final thing then is calibration and relative response. We'll take them one at a time. Calibration. In order to trust the instrument, it has to be calibrated. If I was going to use this instrument in an industrial setting, if I was going to use this instrument in business or industry to make life decisions per OSHA rules, I have to calibrate it before I use it, I have to use it, and then I have to calibrate it after I use it. And if I don't calibrate it before and accurate, I can't say those results were true. Okay, we're not business and industry, we're emergency responders. We will calibrate our instruments once every 30 days because the accuracy, the perfectness doesn't matter to us. All we're going to use these instruments for is idiot lights. It's going to tell us there's a potential problem. It's going to remind us to wear PPE. And so calibrating it once a month in emergency response, it is considered a standard. It's a correct, it's a proper way of doing stuff. That's the calibration. Relative response. If I am an industrial hygienist and I use this instrument in my business to make safe entries into a confined space, I better understand that when I calibrate this to methane, but I'm smelling propane, it's not accurate. And so I have to go into the books and I have to get the response curve and I have to take the actual reading and then I got to times it by a special number for propane because it's calibrated to methane in order to come up with the exact readings. We're emergency responders. I don't care how exact the reading is. The exact reading means nothing to me. All it means And what we're going to use this instrument for is an indication that something is present. If, again, you dive into the relative response curves and you understand them, fine, but you'll eventually come to the conclusion that I don't need to know it as an emergency responder. The information is there. Okay. Unknown gases, unknown atmospheres. When we arrive on the scene of an incident and we're going in on a carbon monoxide leak or a hazardous chemical spill, there's an order to the things that we should be checking for. The rescues have the capability to check for corrosive gases. They should have a little box that's got pH paper in it. So if it's a total unknown atmosphere, they could possibly pull the old pH paper out and determine exactly what's going on as far as corrosive gases go. But the rest of us, the engine companies, the ladder company, we don't carry that. Then we have to get into the order of testing. After we verify there's no corrosive gases, our next thing is to look at oxygen levels, because that's critical. Then we're going to look at flammability levels, because that's the next critical thing to us. Then we're going to look at general toxicity. And if it's a total unknown incident, well, crap, now we could come in with radiological instruments to determine if there's any ionizing radiation or any specialized instruments that we need in order to maybe identify and verify the chemical. So let's go back to the basic ones. Okay, the rescues can check for corrosive gases, especially critical in a confined space. Before I make entry, I may want to just dip the old pH paper into that atmosphere and see if it changes. If not, it's a hazmat team's responsibility. We don't expect everybody to be able to do that. But then we dive into our 5-gas meter. Our 5-gas meter, OSHA. The confined space regulation years ago, 1910-146, began to identify that a monitor, when I'm monitoring a confined space, the first thing we have to look for is oxygen. Well, again, when the regulation was written, many times you had a separate O2 meter and a separate LEL meter and a separate toxic gas meter. And so what they're telling you is the first thing that you always need to monitor for is the O2. Our 5-gas meter monitors everything at the exact same time. But still remember this order. The first most important thing to read is the oxygen sensor. The oxygen sensor is the most critical thing to read first, because if there isn't normal O2 in the air, nothing else is accurate. I'll repeat it. If the O2 is really screwed up, you can't trust the LEL and you can't trust the other 3 sensors. They're inaccurate. Okay, specifically, we all been taught, we've taught for years, 20.9% O2 in the air. When you turn this thing on, when it fresh air calibrates, it should go to 20.9%. Don't get confused. There's other instruments out there that instead of going to 20.9 will go to 21. It doesn't matter. It's close enough. 2 levels. The alarm will go off when oxygen depletes, and the alarm will go off when oxygen enriches. So there's 2 alarm levels on this instrument. Low O2 is 19.5%. The reason it goes at 19.5% is because of an OSHA law. OSHA says when O2 reaches 19.5%, this product is IDLH. Immediately dangerous to life and health. Now that is a legal term. It's got 30 minutes of safety built into it. But it is a term that is used for the average employee at a business or facility. If there is less than 19.5% oxygen in an atmosphere, an employee is not allowed to work in that atmosphere. OSHA says they can't do it. You're not allowed to wear an air purifying respirator with less than 19.5% oxygen in an atmosphere. That's easy. That's their rules. We regularly will enter into atmospheres of less than 19.5%. The alarm level means nothing to us except for the fact that any time the oxygen drops from 20.9 to 20.8, it's a big hint that something else is in the air. I could care less about the alarm. any drop of oxygen should demand that we say something could be present here, and we probably ought to have our SCBA on our face and not take it off until we can verify exactly what's going on. The 19.5%, the reason they set that alarm there is, again, because that's the legal requirement and because the rest of the instruments don't work good in oxygen-deficient atmospheres. They will not work accurately. If I immediately drop the oxygen in this room to 19% by adding nothing more than nitrogen, and we all should be aware that nitrogen is not harmful to us, if I drop the O2 in this room to 19%, you guys would hardly know the difference. Troy might find it harder to stay awake. You might be a little bit more tired. But the bottom line is 19% O2 ain't going to kill anybody. But it's IDLH by OSHA standards. Excess oxygen. The high oxygen alarm is 23.5%. Well, the high oxygen alarm is 23.5% because OSHA says there's a law that says set it at 23.5%. At 23.5%, O2 becomes IDLH, immediately dangerous to life and health. It's a legal requirement. It does not have anything really to do with our health. It's got more to do with the inaccuracy of the instrument in high O2 areas. Look, if I instantly increase the O2 in this room to 50% or 50% O2, nobody would have a problem. Troy would be more awake. He'd be hopping around singing and dancing. If you got a cut, it would even be healing a little bit faster. But the problem is high O2 makes things burn that doesn't normally burn. High O2, here's a word of caution, a side little trip for you guys. You got CPAPs on your medic. Next time you're running CPAP on the medic, think about it and grab the unit off a fire truck and take it with you. And you will be amazed at the high readings of O2 you get in the back of the medic. So remember, you're running CPAP, open the vents, open the windows, turn the fan on, get that oxygen low. High oxygen will allow things to burn that don't normally burn. If you remember back after the evacuation of Katrina, there was a bus of elderly people that were being evacuated that caught fire and it burned up nearly instantly. Well, that's because everybody's in there sucking on O2. The O2 levels were incredibly high in the bus, and when that catches on fire, nobody survives it. You don't even have time to get the heck out of Dodge. Instruments require the O2 to be in that normal area to be accurate. So remember, the idea behind it is O2. It can be adjusted. The way it works is two chemicals that react much like a battery. And when they're at normal O2 and normal temperature, they're going to react at a certain speed. And if they're reacting at that speed, the oxygen level is considered 20.9. But when oxygen drops, they react slower, and the computer gives you lower numbers. When the oxygen increases, they react faster, and the computer gives you higher numbers. That's the way it works. But there's problems with that program. And the reason there's problems is because if I take these two chemicals, if I take that chemical sensor into a cold atmosphere, the cold atmosphere is also going to make the two chemicals react slower. And so a cold atmosphere could tell you, well, there's low O2, but there's really not low O2, it's cold. If you read your directions, it'll tell you there's a temperature that the O2 sensor will freeze. And when it freezes, you don't get a little indication, hey, I'm frozen and not accurate. It just freezes at whatever level it is giving you, and you don't get a change. There is temperature limitations. Atmosphere, elevation, humidity, these are all of the things that can change the O2 level and make it inaccurate. I want to be aware of those things. I know it's tough. You're going to have to start this on a cold winter day in the truck, and then you're going to have to look down and hopefully you're not getting monoxide readings off the truck. And then when you jump out of the truck and you head to the front door, the O2 may change a little bit and you may be totally confused. All I'm telling you is that's the instrument. There's nothing we can do about it. The recommendation is then once you walk in the front door, give this some time to normalize to the temperature in the house and the humidity levels in the house, and then start whatever reading you have there as your potential normal reading. So by the time I fired this up and I enter the front door and I'm standing there for a few minutes and I've got 20.8 on the O2, then consider that your baseline and see if the O2 increases or decreases. That's the O2 sensor. Next up, the next most important thing is the LEL sensor. The next most important thing that this thing is going to read is the potential for combustible gases. Any gas that can ignite and burn can be picked up by these instruments and give you a reading. Now, it can't read combustible dusts in the air, but it can read a combustible gas or a flammable gas that's putting off vapors. It gives you a measurement in something called a percentage of LEL. So let's go back to basic chemistry. Basic chemistry, remember, any product above its flash point is capable of igniting and burning. It just needs a spark. Anytime I'm dealing with a flammable liquid, I have to be concerned about it potentially igniting and sparking. That's flammability. Once it's releasing its vapors, it has to release just enough vapors in order to get it to ignite, and the smallest amount of that concentration in the air is called the lower explosive limit, and the highest amount of explosives in the air is the upper explosive limit. If it's more than that in the air, it can't ignite, it's too rich to burn. The engine of your car is flooded at that point, you can't get it to start. If it's too low or below its LEL, it's too lean to burn, there's not enough product in there to ignite, but anytime it's between the LEL and the UEL, it's perfect, and that's called the flammable range. It's easy to demonstrate. Many times I'll take a little bit of acetone and pour it on the table, and I'll light a match way out here, and nothing happens to the acetone. But as I move closer and closer and closer and closer, when I get about a quarter inch away from the acetone, it'll catch on fire. That point that it caught on fire is its LEL. Well, then I usually talk about the fact that if I'd pour acetone here on the table, I'd pour a whole cup, and I'd back away for 10 or 15 minutes, that LEL would no longer be a quarter of an inch away. That LEL may be 6 inches, it's falling off onto the side, on the floor, onto Eric Keener's lap, and now when I bring my match to it, if all of a sudden I get within that 6 inch, I'm going to get a fireball. Now the fireball is going to be just about big enough that Billy Barber in the back is going to just laugh and giggle. He thinks this is great training, but Eric Keener's not laughing anymore because his eyebrows are singed. It's not funny. If I take enough acetone and I pour it here on the table and I just continue to preach for the next 30 minutes, eventually I can get the LEL all the way over there at the light switch. Now when the light switch is flicked, we don't get a little teeny fire that we go ooh and aw. We don't get a fireball that some of you are enjoying but some of you aren't. We get a fireball instantly the size of this room, and at that point everybody's going to be interested in leaving. The problem is, probably nobody's going to go through the door. Most of you are going to go through the window or through the wall that way or try and get out through the ceiling. If you think about it, which one of those three scenarios are the scenarios that we respond to on a regular basis in a gas leak? Okay, scenario number 3. It's not an incident that just happened. It's an incident that happened and somebody noticed it and somebody called in for help. And now when we're arriving on the scene, we probably have a fairly large fireball. Okay, that's LEL. Well, your air monitor is not going to wait till it gets that dangerous before it alarms. So it measures a percentage of this LEL, and it is going to alarm at 10%. If, and let's hope I can get the mathematical formulas correct, if the LEL of methane is 1.4%, and don't trust me, the number's not important, it may not be 1.4%, then the alarm will go off at 0.14%. That's when the alarm goes off. Great. Why does the alarm go off at 10%? Because OSHA makes it a law. That's all there is to it. It's a law. It is not important for you to remember 10%. If I am an industrial hygienist that I work at a particular facility and we clean the inside of tanker trucks for a living, if that tanker truck had methylethyl ketone in it, then I have to know the exact measurements of how much methylethyl ketone is left inside that tank. If I'm going to send my employees in there, as long as it's less than 9% of the LEL of methylethyl ketone, I can tell my employees, it's your job, get your butt in there and clean it up. Here's the right respirator to wear, here's the right PPE to wear, but get in there and clean it. If, while they're in there, they come upon an area of that tank that is now suddenly 10% of methylethyl ketones LEL, then they have the right to look at me and say, hey, we're on our way out. You cannot make us work in an area that's considered IDLH. It's the law. It's for workers' protection. But again, we're emergency responders. You will find that you regularly go into atmospheres above 10% of the LEL. You're going to do it on a working house fire. You're going to do it on a gas leak. The reading of 1 is enough information for you. Anytime your LEL sensor goes from 0 to 1, it's telling you there is something flammable in the atmosphere, and you better have the right PPE on and you better have a mask on your face. There is no such thing as, hey chief, we're only getting a reading of 10% of the LEL. Is it okay to take a gear off? If I'm measuring a flammable atmosphere and I'm 6 inches away from it before I get a reading of 1 or 2 or 10, great, put the monitor aside and clean up the mess or shut the valve off. But if I'm standing at this door and my gas leak is clear over there in the corner and I'm getting a reading of 1 here at the door, I'm guaranteeing you someplace between here at the door and where that leak is occurring is 2 and 3 and 5 and 10% and 90% and 100% of the LEL. And if the ignition happens back at that point, it's going to blow you back out the door. Now, gas leaks. It's a dangerous occupation. Somebody's got to go in and investigate, but that's why our gas leak SOP says, look, it only takes one company in full firefighting protective clothing and an SCBA to walk in and evaluate. If it's a gas leak, somebody's got to shut the gas off. Great news, sometimes the gas meter's outside. Bad news, sometimes the gas meter's in the basement and somebody's probably going to have to go in and shut it off. Great, it only takes one crew. Everybody else should be in staging, and staging is not at the front door. Your chances of surviving that gas leak explosion at ground zero is better than if you're at the front door where the blast is going to knock you out against the tree across the street. Everybody else goes to staging. That's what the SOP is. LEL, any reading is telling you there's something potentially flammable and I need to have on my full firefighting protective clothing and an SCBA on my face. The LEL sensor, it's got the same inaccuracy. In order for the LEL sensor to work, it's called a Wheatstone bridge. There is 2 little filaments, like light bulb filaments in there. One of them burns in a perfect atmosphere at the same speed all of the time. The other one burns in whatever atmosphere is coming through it. Well, okay. If the atmosphere has something flammable, this little filament burns brighter, the electricity is measured, and it says, hey, there's something flammable in the air, and we get LEL readings. But the problem with the LEL sensor is, if I walk into an atmosphere that doesn't have enough oxygen in it, this sensor will burn dimmer, which will give you negative numbers. Well, there's no such thing as a negative 2 part per million or 2% of something flammable in the air. All it's telling you is the oxygen's screwed up. And if at the same time that the oxygen is a little bit deficient and the LEL is back up a little bit, if I'm at a -2 because of oxygen and a +2 because of the flammable, it's reading 0 on your meter and you're going to think it's safe. It is not safe. Temperature. Really cold weather can slow it down. Really warm weather can speed it up. Elevation. It changes it. We don't have to worry as much about lead vapors from gasoline as we did, but you can still get into an atmosphere if they're using a lot of silicon that it'll ruin and foul up the sensor and it's no longer accurate. So be careful in atmospheres where all of a sudden the meter just doesn't seem to be doing anything. Response factors. This is those relative response curves. We calibrate to methane, correct? It's only 100% accurate when it's smelling methane. When it's smelling propane, it's not 100% accurate, but we're emergency responders. It doesn't matter. Any reading on this is enough to tell the chief, I've got a reading, we've got our full firefighting protective clothing on and our SCBA on, and we're looking for what we can shut off. You have charts. This is a relative response curve. I'm not going to go into it in detail because we don't need it as emergency responders. The third thing that we're there to measure then is toxic atmospheres. Our air monitor is now a 5-gas meter. It measures O2, it measures LEL. The other 3 meters are general toxicity sensors. They are there to measure general toxic substances that are in the air. And we have picked the 5-gas now so that we are now capable of monitoring on a working fire the presence of potentially hydrogen cyanide or potential hydrogen cyanide. The monitors are much more sensitive. They operate in parts per million. But once again, they're telling you that if you get a reading on any of this, you better have on your proper PPE, and the most obvious PPE you ought to have on is a mask on your face, breathing air from the bottle, so that you're not breathing whatever's in this atmosphere. They can also be used to establish the work zones. Great, if I'm getting a high level in the living room, but I'm not getting anything in the bedroom, move operations into the bedroom for these people, or move them to fresh air. The air monitor can be used to help you determine that. Carbon monoxide, hydrogen sulfide, hydrogen cyanide are the 3 things that we are now measuring for. Once again, if I understand their limitations, I can trust the meter better. Carbon monoxide, the most common potential toxic problem out there is carbon monoxide. You all familiar with it? We know the hazards of it. We know the signs and symptoms of it. The thing to remember is anytime I'm burning something or running something, I'm producing carbon monoxide. So the air monitor can pick it up, but the air monitor can be fooled. Once again, temperature changes can make the air monitor give you negative readings or give you false positive readings. So when I started at the front door and it's 30 degrees below 0 outside, and I walk into the house and the heat of the house warms the sensor up, it may go to 1 or 2 or 3 parts per million. Well, I can't help it. It's not accurate. We can't look at the people and say, oh, you got carbon monoxide present, because you don't know it. I like to liken it to this. When I knock on the door and the person meets you at the front door and they're blood red and they're not feeling good and their spouse is upstairs with a headache and they've had a headache over the last 3 days and their 2 kids are unconscious, it's probably carbon monoxide. I don't care what the meter says. If the meter is reading 0, you don't say, well, it isn't carbon monoxide. Go with the signs and symptoms of the victims. If the guy meets you at the front door and he's in okay health, but he just, felt some funny smells, and you walk in and you get a reading of carbon monoxide, you cannot look at them and say, hey, there's carbon monoxide in your house. Because the meter can't tell you that. There are too many things that can fool. One of the most common things that will fool the carbon monoxide sensor is hydrogen gas. If they've got a battery, a lead acid battery being charged downstairs, it's in the basement next to the sump pump, then that lead acid battery charging can produce hydrogen gas, and it will fool the meter and it will give you readings of carbon monoxide. It's not carbon monoxide. It's just fooling you. Now, if you meet you at the front door, they have all these nasty signs and symptoms, and they're beet red and they've got headaches, and you go downstairs and you get close to the furnace and you get a reading of 80 parts per million of carbon monoxide, you're right, that's probably carbon monoxide here. And they probably got a problem. But my answer is always going to be the same. Whether I get a reading or not, let's get you to fresh air and get you to the hospital if you need to, and call in a professional heating contractor to determine if things are operating appropriately. Hydrogen sulfide and carbon monoxide sensor is nearly identical to each other. The only difference is there's a little membrane on the CO that's not supposed to let H2S in, and there's a little membrane on the H2S that's not supposed to allow CO in. But they're not 100% accurate. So even the presence of hydrogen sulfide may fool, and you may also get a reading of carbon monoxide. Hydrogen sulfide, the second thing, the most common in business or industry, the most common in a sewer system, the most common anytime you get a fuel or a diesel leak that's a long-term, is hydrogen sulfide. So that's why that's also included. So industrial chemical, we want to worry about it, but just remember the hydrogen sulfide can be fooled by temperature, it can be fooled by the presence of hydrogen, it can be fooled by the presence of carbon monoxide, and this is not an exhaustive list. There are other chemicals that will fool the CO that will fool the H2S sensor. Finally, because of concern with cancer, because of the fact that we're realizing during overhaul we have some incredible nasty gases, the worst of which is carbon monoxide and hydrogen cyanide, we now have the ability to measure hydrogen cyanide. My personal opinion is I don't need the monitor to tell me it's present, it's present. I joke all the time, the worst hazmat incident that I've personally been a part of is the single-family residence fire. Any working fire, anytime I've got plastics burning, I'm producing hydrogen cyanide, and that's what the studies are finding. Like carbon monoxide, it gets into our blood and tends to want to stay there. And so a little fire in the morning gives us just a little bit, but then by late afternoon, if we get another fire, then we're just adding to it and it's compounding the amount in the body, and the body doesn't get rid of it very easily. So hydrogen cyanide, once again, just remember that the hydrogen cyanide is a sensitive monitor. It's going to measure parts per million and it can be fooled. If you've got it on in a working fire situation during overhaul and you're getting readings of 25, 30, 60 parts per million of it, that's probably exactly what it is. But if you're walking into a house under a foreign odor problem and there's really no signs and symptoms of the people, they just smell something funny, and your hydrogen cyanide starts reading 1 or 2 or 3, don't tell them, well, yeah, you got hydrogen cyanide in here, we better get you out. It's not trustworthy, it's not accurate. That's an overview. The critical part about this is just to understand better the monitor. If I understand it better, I can trust it more. If I realize that it cannot tell me an atmosphere is safe, then I can use it to get good information from it. It will verify what we think we already know. If you have any questions, call us down there at Station 4 and maybe we'll be able to answer it. Call Dave Stevens. Hey, as an additional note, remember, part of intrinsic safety is also the fact that the units sometimes can have interference by radio waves. So if at any point when you key the mic of your walkie-talkie, if you suddenly get an alarm on the instrument, it is simply your walkie-talkie. It's the interference. Typically, if you hold the microphone or the walkie-talkie away from the unit, you're less likely to get that. But also, if you're inside a confined space, the keying of a mic will likely set the unit into an alarm. Once you release the mic, you'll eliminate the alarm system. So don't allow that to cause that false alarm to cause you problems.
Standing cup. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118 The P400 is a multi-gas monitor. What it does have are 2 buttons on the left. They're arrow buttons that will let you scroll through different programs. On the right side of the monitor, you got an O button and an X button. The O button is to turn it on or to enter into a program. The X button is to X out of a program once you get into the different areas of it. The front has a protective screen to help the sensors from keep the sensors from getting dirty. Trying to take it off here. Of course, it won't come off. Are you kidding me? It has a little air conditioner filter is all it is, and all it does is help protect the sensors. If this would get dirty, all you do is rinse it out with clean water, let it dry good, use a paper towel, squeeze the water out of it. Once it's dry, you can put it back in, put the cover back on, you're good to go. The batteries, just the 4 screws. Take the cover off. The cover, you got to be kind of careful because it has 2 little plastic clips on the back side, and they're easy to break, so you kind of have to be gentle when you put the cover back on. It's just 4 AA batteries. Those can be replaced at the station level. To turn it on, you just push the O button. It takes 2.5 minutes for it to warm up. Let me put this back on. While it's warming up, it'll tell you the system, the time, the date. Then it'll go through a systems check. It'll check the lights, make sure the lights are all work. It'll have a sounder to make sure the sounder works. It'll have the vibration to let you know there's another thing to let you know that everything's working. Then it'll warm up the sensors. It warms all the sensors up, auto zeros, so once it's warmed up, normally you'll be able to just go in and use it. I'm waiting for the sensors to warm up. Like I said, it takes a little while, especially when you're on a run. Now the sensors are warmed up, it's auto-zeroing the sensors. It's adjusting to the atmosphere that it's in right now. If you go from a real, and it will tell you what sensors are in it, and if it passed or not, and how soon it's due for calibration. Once it goes through all those steps, it will give you your home screen. It will give you the time at the top left, your battery volts on the top right. At 4.8 volts, it's recommended to replace the batteries. Like I said, it is 4 AA's. At 4.8 volts, you should be able to get 8 hours out of the unit. Anything less than that, you won't have time probably if you had a working incident, but at 4.8 volts you'll get 8 hours. The rescue companies, they should replace them at 5 volts for the fact they use a pump, and the pump just draws on the battery so much. On the front, the 4 brass looking connections are for the pump. They'll just sits on there and twists, put it on. The far right side, beside your percentages, there's a T. And under the T, it'll tell you percentage of LELs, parts per million, And what that does is it just gives you a heads up. Once you start getting into a product or whatever it is, that will start flashing just to give you a heads up, hey, you're getting into something. Once it reaches 100%, your lower LEL will go into an alarm. So it's just a heads up, it's immediate detection to let you know that something's going on. Filter is like an air conditioner filter. If it gets dirty, whatever, you can take the 2 screws out, pop the cover off, and this is just a little filter. To clean it, it's just warm water, no soap, just rinse it out good, let it dry. I put it in a paper towel, make sure all the water's squeezed out, and then you can put it back in and then put your cover back on. All it does is help protect the sensors to keep them from getting dirty. That's all that does. If you have any questions, feel free to give me a call. I'm at 75252. Thank you.